Welcome to qnawire.
This is problem 66 of chapter 23. In this problem, we're asked to determine how close can two sunspots be such that our telescope is still going to be able to resolve them. So the diameter of our objective lens is given as 20 centimeters. So we're going to go ahead and convert this to meters. 20 centimeters is 20 times 10 to the negative 2 meters. And we're also given the distance between the Earth and the Sun. So we're going to call that capital R, 1.5 times 10 to the 11 meters. So to determine the resolution limit, we're going to use the following equation. Theta res is going to be equal to 1.22 lambda over d, where d is the diameter of the aperture. In this case, that opening is going to be determined by the diameter of the lens of the telescope here, capital D. So this problem, here we are, let's go ahead and draw a picture. Here we are on Earth, and then we have the Sun a distance r away, and we are told that sunspots appear in pairs. So here we have two sunspots, let's say, and let's go ahead and draw some lines from Earth to those sunspots. So this is what our telescope is going to be observing. So here, let me go ahead and change the color to distinguish between them. So this angle, that is the angle of resolution that can be resolved. However close these objects can be placed such that they are still distinguishable, that is our angle theta res. That is our resolution limit. So here, this is our angle theta. So this is theta res. So theta res is the angle such that this distance is minimized and the two sunspots can still be resolved with the telescope with this objective lens diameter. Okay, so from here we see that we're going to be using small angle approximation. So here we could determine that distance. So here, let's go ahead and draw a line between these 2 points here. So because r is so large compared to this, we can use the definition of an angle to say that, and we could treat this as a sort of arc. We can go ahead and treat this as a sort of arc, and we can say that tangent of theta res is approximately going to be equal to theta res. And then we'll use the definition of angle to say arc length. So here, this separation, we could call that little d, over this radius. So the radius here of the arc would correspond to the distance between the Earth and the Sun, capital R. So that's this, and we could call that separation d, which is the arc length, or we could call it d. Either way you look at it, the result is still going to be the same, because tangent of theta, if you suppose that this was a straight line, then opposite over adjacent is just going to be d over r, which is the same thing here. So here we're going to multiply both sides by r so that we could get d. D is the separation distance, that's just going to be r times theta res. And we know theta res from this expression, so let's go ahead and type that in. Let's go ahead and grab this. So we know r and we know d. The only thing we don't know is lambda. So we are going to get lambda based on the visible light. We know that lambda of visible light, lambda vis, is between two bounds for the visible spectrum. And on the lower end, we have 380 nanometers. On the upper end, we have 740 nanometers. So the average here, let's call this lambda average. The average of these two extremes comes out to be 560 nanometers. Now, for this problem, we're asked to give any assumptions that we've made. So this would be one of our assumptions. We are using the average wavelength for the visible spectrum. So this comes out to greenish light. If we plug this in here, we would get that resolution distance. Let's go ahead and do that. Our radius, or distance from Earth to Sun, capital R, is that. This is going to be multiplied by 1.22, our wavelength, and this is our wavelength, so we could write that as 560 times 10 to the negative 9 nanometer. Meters, rather. We're converting from nanometers to meters. So here it is. And capital D, which is the diameter of the objective lens. Meters cancels out with meters here, and we're going to have 1 meter left over, so our final unit is going to be in meters. So when we multiply all this out, we get approximately 512,400 meters. So in kilometers, this is approximately. So let's round to 2 significant digits. This is approximately, let's call this 512 kilometers. So we can resolve sunspots whose distance from one another is 512 kilometers or greater, assuming we're using light of wavelength 560 nanometers. Notice that D is proportional to lambda, so if we use visible light on the lower end, we're going to get a more powerful telescope based on this equation. If we use light on the higher end, here this distance is going to increase. Whatever lambda you use, it should be between these two extremes for visible light, but it should be on this order of magnitude. So this concludes problem 66.